All right. If everything goes as planned today, or today for this video, I should say, then this might be the last video that we have for OChem 2, but we'll know here. You know, as you guys might have noticed, I know it's been odd with the online class, and sometimes I have a tendency to ramble, so I'm going to try and keep the videos, you know, to about 30 minutes. But we'll see how it goes. But we are in chapter 22, and chapter 22 is talking about amines, and it's kind of, to be honest, it's broken down into really only two parts, which is stuff that you already know, and then, oh yeah, we should talk about this also, right? So we'll start out with the stuff that we already know, and then we'll add a couple of new things there at the end. Let me double check here before I say this. There's really not any new mechanisms to learn in this chapter, which some of you guys might be cheering. Now remember, when I say this, I always should put that in the context of the mechanisms that I require students to memorize. Right now, obviously, you guys are at home, and you know we're doing open book exams, all that kind of stuff, so you don't have to memorize anything. So really, I should say the mechanisms in here are not, you know, something that we'll see broadly applied in other parts, is what I mean, right? For instance, an Sn2 mechanism, we see it all over the place, right? The thionyl chloride mechanism, you know, we see it maybe a couple of times, but not nearly as important or prevalent as the Sn2 steps are, right? So that's kind of what I mean with that. See what I said about rambling? Let's get to it. Okay, so how can we make some amines? Well, speaking of Sn2s, right? We learned this one a while ago. We can add a cyano group in there, right? That's nice. Whoops. And I almost did exactly what I was about to warn you guys for there, right? So be careful. Ooh. Be careful when you guys are doing this, right? That we, remember when you add a cyano, we're adding one additional carbon also, right? So there it is. And then if I take this and I give it the old LAH treatment, right? I give it the old LAH treatment. And we do, remember, we have to finish this up with water. That's going to be something kind of important just to keep in mind. If we do this, then we will end up reducing the cyano to the primary amine. So why do we have to use water? Normally we could use acid there. Well, this is one of the properties of amines, is that they are basic, right? So if you did this under acidic media, then you would end up protonating this and make the ammonium salt, which then you'd have to come back and deprotonate, which you could do it, and honestly, that's probably how we would clean this up. Different argument for a different time, right? But just remember, you know, one of these kind of points is to use water instead here, okay? Great, Sn2 reaction, LAH reduction. Remember, nitrile is very similar to carbonyls. We have a carbon that's bound through pi bonds to an electronegative atom, basic conditions versus acidic conditions, all this kind of stuff that comes with it, okay? Good stuff. The other way that we learned, or another method we have, is if we instead, right, we could start with a carboxylic acid, we could soakle it up, right? Use a little thionyl chloride here. Chloride, add an excess of the amine, right, to make the amide. I ran out of space. Let's just move this over. Uh-oh. Technical problems. There it is. Okay. So carboxylic acid, acyl halide with ammonia to make the amide. In the amide, we can again, I don't know why I was trying to do that. LAH it up, some water, and we will end up with the amine once again. Fantastic. What's the benefit of this? Well, we don't add any carbons, so as many carbons as we start out with is as many as we end up with, right? So remember, up here we add a carbon to it, so just have to make sure that we're keeping count on that, okay? Good, right? This is just one of the many ways we could do this. There's a couple other in here. I'm not going to sit here and copy everything out of the book. You guys can read through that on your own, to be honest, right? There's plenty for you guys to look through, right? Just for argument's sake, though. Nitration, here's one of the mechanisms we had already this semester, right? The aromatic substitutions. We had the nitro, we can come back and reduce that. There's quite a few ways we can reduce this, to be honest. HCl and zinc or iron or, I don't know, you could probably find some other metals to come back and do that. But tin works fine for this. So really, any of these metals that are very prone to losing electrons is kind of what it is. Iron, zinc, tin, probably could find something else, right? But that'll take this down into the amine. So remember the difference, or one of the differences being that on an aromatic system, right, we can't really do Sn2s, so we can't bring in a cyano and this kind of stuff. Although we will learn how we can do this in just a little bit, okay? But there's another method there of doing it, right? Fantastic. Okay. Now let's kind of go back and keep on reviewing here. We'll go back to my favorite reaction, which is the Schiff base. And like I said, it's just my favorite just because of, you know, one of the first reactions I did when I was in the lab to make something new. Now, if a Schiff base, in essence, is if we, let's just go ahead and be concrete about it, right? If we take some kind of amine with a ketone or aldehyde, right? And we put a little bit of acid in there. It's the catalytic amount of acid, just a little scoop of the p-toluene sulfonic acid is kind of what I always used. What you'll end up doing is making the, you're making the imine. So we end up swapping the carbonyl oxygen for the nitrogen. Great. Now, if we could just reduce that double bond, then we could end up making an amine, right? Which would be great. So we'll find some kind of reducing agent here, right? And we could end up making the amine, which would be great. Now, why is this useful for us? Now, let's think about this for just a second, right? Because remember, you're like, whatever, right? We just made another amine. Get to the point. Well, take a look at what some of the limitations are with the other methods that we have, right? So especially here, right? So what's the limitation of this route? Well, the limitation there is we have to be able to do an Sn2 reaction. Now, where do Sn2 reactions work? Well, they work primarily at primary alkyl halides, right, or primary leaving groups. With a carboxylic acid, right, we have to use thionyl chloride, which honestly isn't all that selective, right? If we have other groups in the rest of this molecule, right, the thionyl chloride could react with those. And we also have to have a carboxylic acid to begin with, right? And then we can turn that into an amine after we use something like LAH, right? We have LAH in both of these cases, right? That's harsh reducing agents, right? Those are harsh reducing agents. Here, this is exclusive to aromatic systems, and the reduction isn't selective, right? This is very close to our, not Burt's reduction, oh my gosh, I'm forgetting the name at the moment. Where we can remove I forget the name, I'm sorry, I apologize. But where we can remove the carbonyls that we add through the Friedel-Crafts acylation, right? With a zinc mercury amalgam, right? So somebody will find it. It's in one of the previous videos. But what I'm trying to think of, the name here, the Wolff-Kishner, right? Yeah, Wolff-Kishner. No, I forget. Now I'm just making it worse. But that is the reaction that I'm thinking of here, right? We can reduce our carbonyls with this same setup. So if we wanted to make an amine, right, we can't do this method of reduction if there's a ketone around or anything like that either. That's the point, right? So we're trying to find something that's selective. The other point is, think about it, right? If we're doing this with a ketone, this is at a secondary position. So we can't go through the cyano method and then the reduction of it, okay? Plus, to finally drive the point home, this is a ketone. We just spent essentially 2 chapters talking about how to make ketones, how to add them, how to change them into a different functional group, how to do important stuff with them. Here's another way we have, right? And in fact, this is a very common way, right? So ammonia to this. The reducing agent we're going to use here is sodium cyanoborohydride, right? So cyanoborohydride, so NaBH3, okay, Cn, okay? Cool. Sodium cyanoborohydride, right? Now very close to borohydride, sodium borohydride, NaBH4. Now, what's useful about this? Well, we add that cyano group in here, and that changes the electronics. These hydrides aren't as hydride-y. Is that a word? Right? These hydrides aren't as strong of a base or as strong of a reducing agent as they are in sodium borohydride, right? Which allows us to do two things. One, this will not reduce a ketone. It's selective. That should be very important for you to kind of like, oh yeah, that's important, right? And we can actually lump this all together in one reaction, which is also extremely useful. What I mean is this. We can put this together. We can put the ammonia with some acid with the cyanoborohydride. Okay? And at the end of the day, that's what we will end up making. That's really darn useful, right? Why? Because we can just dump all this stuff together at once. Okay? Chemists are lazy. They're going, oh, I don't want to do 2 steps, I want to do 1. Okay, well, here you go. Here's a method that we have of doing it, right? So, in 1 step, we can mix all this stuff to turn a ketone into an amine. Very, very useful for us, okay? And this can work not only with ammonia, it can work with pretty much any amine that you guys have, right? It'll go through and do what you need to with that, okay? Obviously not tertiary amines. Tertiary amines won't do anything, but secondary and primary amines will, okay? Very, very nice. That's good. So let's spend a little bit of time. We got about 15 minutes left here, right? Let's spend a little bit of time talking about something new with these. And this is the really important part of this chapter here, okay? Predominantly, once I have an aromatic amine, what I can do is turn this into a diazonium. Now, what in the world is a diazonium? Well, it's this, right? That's what a diazonium is. Now you might look at that and say that doesn't look very stable at all. And the answer is yes and no, right? And because of yes and no is why we kind of are limited to dealing with aromatic compounds. Although for any of you who are interested in this kind of stuff, if you go look in the scientific literature, you can see where these are applied to some degree to alkyl and non-aromatic systems, although it's difficult to do, okay? Here's why. So if I ignore this for a second, so what do I have here? That is basically N2 as a gas, right? That is N2 that is bound, right? If I could kick this off, I would release N2 as a gas. That's huge. Why? 2 things. This is a fantastic leaving group. Because it produces a neutral compound, right? If I take those electrons with me, remember the electrons will go to the more electronegative atom, right? That just makes sense. Nitrogen's more electronegative than carbon, right? Nitrogen's going to take them, right? So I kick off a neutral leaving group. That is a gas that is completely unreactive, right? That is like the dream leaving group right there. Because you don't have to worry about cleaning this up. It just bubbles out of solution. We don't run anything at cold enough temperatures to trap nitrogen as a liquid. And even then, you just have to warm it up and it will bubble itself out, right? So this is a fantastic leaving group, which makes it very reactive, which makes it difficult to isolate. Because if you think about it, the reason why, or one of the reasons why, this doesn't just leave is because then you end up with a carbocation on a benzene ring. Not a very stable situation, right? So that's the reason why. But on an alkyl group with all the stuff and the shifts and the rearrangements, all that kind of stuff, that makes them far more reactive, right? So we're kind of limiting ourselves here. And these are actually surprisingly easy to make. We need sodium nitrite, NaNO2, and some HCl, so sodium nitrite, okay? And and it shows the mechanism of how this works. Look it up, it's interesting, right? Well, we end up with this. Who cares, you might say? Well, because this is such a good leaving group, we can do a lot with this, all right? So let's take a look at all the things we can do. So we'll do this. Okay. And we start to pick some colors. If I start to mix this with different copper salts, so copper, and we'll do X, where X equals Br or Cl or I, right? So copper 1 chloride, bromide, or iodide. I can swap that out to make a halogen, right? So I can swap an amine on an aromatic ring for a halogen now, right? Just by using a simple copper salt, okay? Or X can also equal a cyano, right? So copper 1 cyanide, and I can swap in a cyano group in there. Now, why might that be useful? Well, remember, this comes from an amine. If I swap it out for a cyano and then reduce it, I can turn it into a methyl and then an amine, right? So I can add 1 carbon and basically just move the amine over, right? So let me just visualize this for you guys here for a minute. Right, we start out with this, right? Here's what I'm asking. How can I turn that into this, right? We start out with this. We can go through the diazonium here. We add the cyano, and then we reduce that, and we can end up putting a methylene group in between there. That's pretty darn. Now, is that the only way to do this? No, of course not, right? But here's one way of doing it there, right? So see if you guys can fill in what that is there, right? It'd be good practice, okay? So any of the halides, chloride, bromide, or iodide. Oops. Start out with that diazonium there, okay? We can put in some water. This one's always useful. Some water, and we kind of heat this up. And what we end up is making an OH. Now, why is this useful for us? Well, what is the only other way we had of adding an OH so far? Really, the only other way we had of adding an OH is going through a nucleophilic aromatic substitution, where we had to have a bunch of withdrawing groups on the ring, and we could add in some hydroxide and really kind of heat that up. But here, like, we could almost do this at room temperature. You might have to heat it up a bit, right? But now we can swap an amine for an OH. Very, 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 very useful for us to be able to do, right? We could swap this for a, watch, this one's always cool. We could swap it for a hydrogen. If we use a, yes? Yeah. H3PO2, right? Now, why is this useful for us? Well, think about it. Remember, this all starts from an amine, and we end up swapping out an amine for a hydrogen. So now we could even use an amine as a blocking group. We can use an amine to activate a ring. We can turn it into a diazonium and kick it off back to the hydrogen, and we remove that amine, and the ring isn't activated anymore, right? So if we need a reaction to get going, we can activate the ring and then remove it later on, just by simply adding some acid. Truth be told, you can add different acids here also. If you look online, there's a bunch of different ones you can add. It's really not all that selective, and I don't know why the book particularly picks this, although I have my suspicions as to why. It doesn't matter too much, okay? All right, and then we have probably the most useful one. We can end up swapping it for a fluorine. If all we got to put in there is HBF4. Now we can put a fluorine on a ring. Have we learned how to add a fluorine? The answer is not really. Now, why is this important? Well, it's important for a number of reasons. For any of you, allow me to ramble for a bit. For any of you who are interested in going into the pharmaceutical industry or being a synthetic chemist, fluorine chemistry is a highly sought after skill for any of you guys going into the pharmaceutical industry, right? Being a fluorine chemist and working with it and understanding it and all that kind of stuff, right? A lot of the most common pharmaceuticals tend to have fluorines in them just because they're properties that they impart, right? And we could spend a lot of time talking about that. I'm trying to keep this short here, right? But so far, we really haven't talked much about fluorine, especially not how to add it, right? But this is right now is a very simple and effective and relatively easy way of adding a fluorine to a benzene ring, right? So extremely important. So now we've expanded to cover every halogen, right? We can add cyanos, an OH, also not that easy to do, and we can even get rid of it and replace it with a hydrogen there, right? So extremely useful functional group there to be able to do that diazonium. Now, the rest of this chapter is basically just kind of dealing with some of the other bits and pieces of what we can do with amine chemistry. But this is the main part that I really wanted to talk to you guys about, just what we can do with these diazoniums. And I almost brought this back into the aromatic chapter, but because we're doing this all online, I didn't want to jump around in the book too much. So really, you know, if it were me and taking notes, I would put this in my notes with the aromatic chapter there. That's really where it fits, to be honest. Okay? But that's it. Awesome. Thank you guys for sticking with me for the summer here. And I'll be in touch through Canvas, and we'll see where we're going to go from here. All right.